What is going on, guys? Welcome back to my channel. This is Darian the Dev, and you guys are tuned in for week number 6 of the Career Progression live stream, where every week myself and some other professional software developers go through our self-paced, self-taught curriculum, or whatever you guys want to call it, learning strategy to basically keeping ourselves competitive and getting new skills as software developers. And, also bootcamp graduates. Both of us also graduated from coding bootcamps. So this week, we're going to be going over design patterns in operating systems. So I'm super excited. If you guys are into tech, coding, entrepreneurship, or startups, make sure you like, share, and subscribe. It really helps me to stay motivated to keep making this content for you guys. And that's pretty much all I talk about on this channel. That's all the videos are about on this channel. So we're going to start in just a second here. If you guys have any questions or anything like that, make sure you drop them down in the comment section down below, and we'll do our best to answer them while we are on the stream. So let me see. Go ahead and get everything set up. Let me make sure that the stream is going good on my phone really quickly. I appreciate y'all for joining as well too. Anybody who's here with me on the stream. So let's see. And there we go. All right, cool. There we go. All right, so let me go ahead and call in our guest. So I'll give her just a second. Not sure if she's ready just yet. Try to call her one more time. Let's see. Alright, let's see. La.
Hey.
Hey, there you go. Okay, I can see you. What's going on?
Not much. What's going on with you?
Nothing. I was just about to call you. I was like, I wonder if if her alarm didn't go off. It's like, let me call her.
No, it went up. I was getting something to eat. Sorry.
You're good. I'm just giving you a hard time. All right, cool. So, I'm gonna go ahead and share my screen. We can get this thing started. I want to go here and options live demo. I want to turn on my live demo. Okay, so drag this over. So I don't know if do you have the stream on YouTube, or are you just on Skype?
Let me turn on YouTube.
Okay. Let me know if you can see my slides. Yeah, oh yep, we're good. I can see him. So this week I'm gonna be going over design patterns, and I actually excluded my code examples. There's one that has a code example because it's pretty straightforward, but for the sake of time, I just wanted to go ahead and do like a high level overview of some common design patterns. So we're gonna talk about the 3 types of design patterns that there are, and then there's 2 examples of each of those types of design patterns. So there's 6 altogether, and yeah, if anybody has any questions or anything like that, leave them in the comment section down below, and let's jump into it. So a design pattern is a tested solution to a standard programming problem. So it's meant for us not to reinvent the wheel or for our code to be spaghetti code and our apps to be huge monolithic apps. It gives us a way of other people, if they're familiar with the same problems or the same design patterns, then our code will be like self-documenting, so that other people can understand why we have certain things set up the way they are, why we're using a certain design pattern, the purpose of it. So they're intended to help handle change as developers face unforeseen circumstances. So as things come up, as requirements change from the business, we want to be able to either add functionality or remove certain things or extend certain things, and we want that to be as easy and seamless as possible. If we want to switch something out or use something new, we want that to have as little impact on our existing code base as possible. So if we have design patterns in place, then we know that we're following single responsibility and we're keeping all of our concerns separated, and everything is designed in a way that if we do something over here, it won't break something over there, or at least it'll help us not to do that. So we talked about these types of design patterns. So the 3, has a regular because the connection was not fast enough. Alright. Let me see. Like, can you still see my screen?
I can see it, but
so bad connection right now. So I'm going to. Yeah, is it still frozen on your end?
Yeah, it's still frozen on my end.
Trying to see if there's a way I can stop some other processes or something so that.
Yeah.
Let's see. Kill that.
We're back.
You said we're back?
It just says design pattern. That's it.
You said it just says design patterns?
And now it's back to your creational, behavioral, and structural. I can see that.
Okay, I think we're back. I'm looking at it right now. It's got an odd delay. So sorry anybody is watching. I'm getting on my end. It's saying that my internet connection is not fast enough right now. So yeah. All right. So do you see creational, behavioral, and structural on your end, La?
Yes.
All right. Cool. So these are 3 types of design patterns: creational, behavioral, and structural. And let me see. All right. So we're gonna start off with the behavioral ones. So behavioral design patterns are meant to be concerned with algorithms and the assignment of responsibilities between objects. So that is the sole purpose for any design pattern that is technically deemed a behavioral pattern. And so the 2 we're going to look at are the observer and the chain of responsibility, because I think there is two cool ways of looking at different behaviors in a similar way so that we can understand how different behaviors can work. So in this case, we're going to, talk about the definition of an observer pattern. So the observer pattern is a behavioral design pattern that lets you define a subscription mechanism to notify multiple objects about any event that happens to the object that they're observing. So in this case, the observer pattern and the chain of responsibility pattern are going to be two different ways of looking at doing the same thing, which is these notifications and subscriber type concepts. The difference is going to be notifications in parallel, which you're going to see with the observer pattern, and then notifications in a series in the chain of responsibility pattern. So I think it's cool to see that we can think about what our app needs to do, and we can make that decision. Do we want everybody to get notified at the same time, or do we only want certain people to get notified if the notification is applicable to them? And if we think about how we want the app to work, then we can decide between if we wanted to use something like an observer or a chain of responsibility. So we'll look at how that works. So in the observer pattern, like we said, we have a subject, and then there's a notification that gets sent out to anybody that's subscribed. So this is a parallel example of notification. So everybody's getting notified at the same time. As soon as something happens with this subject, everybody's going to get the notification. So if we think about it like a database, then our subject, object or class would be our database. And then let's say that anytime there's a change in the database, we want somebody or a certain, role of a user to get notified whenever there's a change to the database. So if there was, let's say, an administrator, a manager, and a boss. So let's say if we had 3 different subscribers, we had the administrator, the boss, and the manager, and all 3 of these people needed to know every time something changed in the database, we could use an observer pattern, create the boss, the manager, and the administrator as a subscriber, allow them to subscribe to the subject, and anytime something changes with our database or our subject, then that notification will automatically go to all 3 of them. So that's how we would do that in parallel. So if we look at the chain of responsibility design pattern, we'll see how we can do that in a series. So the chain of responsibility pattern lets you pass requests along a chain of handlers, and upon receiving the request, each handler decides either to process the request or to pass it to the next handler in the chain. So again, this is going by who needs to know about this notification. So it's not something changed, let me notify everybody. It's instead something changed, so who needs to know about it? So in this case, it's a series, like we said. So this is, if we had the same example, if we went boss, manager, administrator, and the subject is our database, let's say not everybody needs to know that the database changed, or if everybody needs to get a different message. So let's say that the notification was an email, and the email needs to go to the boss, the administrator, and the manager, but it's a different email based on who they are. Then we could use this, and anytime something changes in our subject, it looks at the first object. So let's say that's the boss, and then we can send that boss a certain type of subject, and then it can go to the next one and see what type of role that person is. So if they're a manager, then it sends them something different. And we can do this in a series instead of doing it in parallel, or we can skip over people. So if we don't want everybody to be notified, for example, if only the administrator needed to know whenever something changed in the database, then if our object 1 was a boss, they wouldn't get notified. It would look at it and say, okay, you're not the administrator. It would pass it to the next handler, which would be the manager handler for object 2. If you're not the administrator, it's going to pass it to object 3. It's going to look and see if you are the administrator. If you are, it'll send you the email that something changed in the database. So the next type of design pattern is structural. So structural design patterns explain how to assemble objects and classes into larger structures while keeping these structures flexible and efficient. So these I'm still getting better on myself, honestly. So these examples are actually a little bit shorter because I didn't want to put anything here I wasn't confident about. But we'll look at how these can help maintain the best use of your processing power and memory on your computer if you use these design patterns. So examples are going to be the decorator pattern and the fly weight pattern. So first one's going to be the decorator. The decorator allows you to add additional functionality or responsibilities to an object dynamically. So that sounds pretty standard. So to make that make more sense, we got to talk about wrapper classes. So wrappers are classes that take an instance of another class. So in their constructor, you're going to pass in a different class. But the wrapper class then is meant to expose the desired features and build on top of that class, basically. So you can literally wrap another class in this class and then give this class additional functionality. And this, again, just helps keep single responsibility in play. It helps your code be readable. And there's also a lot of other benefits for like speed, efficiency, and memory, garbage collection, all that good stuff, purposes that I'm not the best at yet. So I'm not going to speak on those things or go super in depth on those things. But yeah, that's the benefit of using this type of design pattern, is breaking concrete classes, if you want to extend them or give them more functionality, using patterns like decorators to use wrapper classes to give them extended functionality so that your code doesn't get messy and your concrete classes get super big and everything is all dependent on each other. So if we look at this is a good example. So I just put screenshots in here because I thought it was good. So if we had an old school application that only had one way of sending out notifications to people in our application, our users, right? So if we had like this one generic notifier class and it had a method of sending some sort of message, it had a send method that we could pass a message into, it sends the message out. But if that notifier class only sent emails to everybody, that would be a problem, right? If we wanted to build on top of that, we wanted to say, well, instead of just emails, we want them to be able to do or be notified some other way besides just emails, then this class is not set up for them to do that at all. So let's say this is an example of what we want to do, right? So our system right now only can send emails, but we want our program to be able to send text messages. We want them to be able to get notified by Facebook. We want them to get notified by Slack, just based on, people's preferences or what group they're on within the organization. We want them to, have different ways of getting notified, or multiple ways, not just email. So we could do this in a naive way like this, which would be to basically make new classes for each way of doing it. So we'd make a SMS notifier class, a Facebook notifier class, a Slack notifier class, and then inside of there we would be we'd be calling a bunch of different methods and trying to chain things together to make all these notifications work together. So we'd be trying to call SMSs and Slack notifications together, and SMSs with Facebook notifications, and we'd have a whole bunch of recycled code, duplicated code in a whole bunch of excess classes that would just make our code way harder to follow for developers that didn't know what we were trying to do. So this would be the better way of doing it. So what we would do is we would make decorator classes that would basically wrap our notifier class. So we would just pass in a notifier. So our original notifier that only sent emails, we could wrap that class inside of a decorator class, and then from there we could make 3 different classes instead of however many we had in that last example. We could make 3 decorators that basically would extend the base decorator class, or we could change how the send message works. So instead of sending just emails, in the SMS decorator it can send a text. In the Facebook decorator it can send some sort of Facebook notification. In the Slack decorator it can send a Slack message. But again, we just basically reduced the redundancy of the code and just kept it in a more readable way. There's also performance benefits, but like I said, I'm not the person to speak on that. So the next one is the flight weight pattern. Again, this one's really interesting. I think you might find this interesting because it kind of gets down to like lower level stuff, like memory. But I need to do more research before I can go way more in depth on this one. But I thought it was definitely worth mentioning in terms of a structural pattern and some of the ones that exist to really help us get the most out of our machine, basically. So the flight weight pattern fits more objects into the available RAM by sharing common parts of state between multiple objects instead of keeping all the data in each object. So I know that's like That sounds like a lot. So fits more objects into the available RAM by sharing common parts of state between multiple objects instead of keeping all data in each object. So basically, we're breaking up our objects into what is going to change and what's unique to the object itself, and we're deciding where we want to save that data. So certain data we're going to put in our RAM, and then the other data we're going to keep somewhere else, but together this design pattern is going to help our program run faster, and it's going to make better use of our memory. So to understand this pattern, you have to understand intrinsic versus extrinsic state. And again, like I said, I'm not an expert on it, but these are the two types of data that we're going to separate in order to get the performance benefits of the flight weight pattern. So the intrinsic state is fields containing unchanging data duplicated across many objects. So intrinsic, like inherently belonging to the object, anything that is not going to change, but every object is going to have it. If we had a bunch of instances of the same object, if all of them are going to have some sort of common data across all of them, that's the intrinsic state. It's the inherent, state of the object itself, if that makes sense. And then we have the extrinsic state, which are fields that contain contextual data that are unique to each object. So this would be what could change based, from object to object. So the difference, I guess the big difference in the flyweight pattern is how we separate this, these two types of data to maximize our memory and performance benefits. All right, so there's the creational pattern and the creational types of design patterns, which provide various object creation mechanisms that increase flexibility and reuse of existing code. So I think these are the ones that I've probably run into the most at jobs and just in the professional world, are creational design patterns, because there's a lot of data moving around, a lot of different things that are created as objects. And yeah, so I guess that's why, thinking back in hindsight, a lot of those patterns are in place. So we're going to talk about these two. Singleton I actually first encountered in my final project in Coding Bootcamp. Is the first design pattern I think I was really ever exposed to. And then factory is also super, super common. I've seen it in every professional code base I've seen so far. So yeah, so these are both really, really common ones, but they're both examples of creational design patterns. So we'll talk about the factory real quick. So the factory provides an interface for creating objects in a superclass, but allows subclasses to alter the types of objects that will be created. So that might sound like a handful, but the next slide, I promise, is going to clarify all of this, and then we're going to move on, because it's actually as simple as it's going to sound. Because it literally
we're not seeing your slide. I don't see a slide yet. Intrinsic state.
Oh, okay. So I'll go back. I'll keep it here.
I still don't see. I'm still at extrinsic state. There you go. Creational.
Nope. So there's a lag. It should move forward. I can tell. I'm looking at the stream health. It's probably just a little bit behind.
Okay.
But yeah. So basically, the slide I'm on, for anybody that can't see it, yep, because I see the stream is still a little bit behind. But the factory pattern provides an interface for creating objects in a superclass, but allows the subclasses to alter the types of objects that will be created. So we basically just outsource the decision of what type of object gets created. We just pass it to a factory method, and it decides what type of object we need based on something else that we pass it. So basically, we just create objects in an interface instead of using the new operator. And that is literally the definition, or the simplified definition of the factory pattern. Create the objects in an interface instead of using a new operator. And again, we can get wild with that. We can create factory methods that, like I said, makes decisions for us. So if we have a database connection and we need to know what type of database connection, we have multiple database connections and we need to know which type of database connection to create on the fly, we can pass a database object through to a factory method, and based on what type of database object we pass it, it will know, or it can handle which type of database interface to create, whether that's MySQL, MongoDB, or whatever else you're using, for example. But we can outsource the decision making of that to one factory interface, or however you want to name it. But if we use the factory method, we can make that much simpler in our code. The last one is going to be the singleton design pattern, which, like I said, was the first one I learned. If you're in bootcamp, or if you're going to a bootcamp, you're more than likely going to run into this one. Super common. The singleton ensures that a class has only one instance while providing a global access point to this instance. So there can only be one type or one instance of this class ever created in your program, and then the whole rest of the program has to utilize that one instance. There can never be more than that one. So this is commonly used for databases, or for certain types of files. So there might be, like I said, a certain file or a certain database object that you don't want a bunch of them getting created. This goes back to like memory usage type stuff. We don't want to create a whole bunch of database objects that could get really big, especially depending on what type of data we're passing and how big the data is. We don't want a whole bunch of database objects or database connections flying around in our code and soaking up all of our processing power. So if we want to make sure that that doesn't happen, we can use this design pattern. And this is actually a code example of how that would look. So this is actually in C#, but hopefully anybody who knows Java or is learning Java can understand. But I didn't want to use a bunch of code examples because I wanted people to be able to go and look and see for whatever language how it works. But in this case, I thought this was a good, really straightforward example. So in our singleton class, our instance or our constructor of the singleton object has to be private. So this is how we prevent any other instances of it getting created, because this can only be created if another class has access to the singleton class. So it's a private constructor, and then we set the only instance there can ever be of this class to a variable called instance in this scenario right here. So, and it's also private, right? So so this variable instance holds our only instance of the singleton. And like I said, these are both private, so these can only be accessed by classes that have access to the singleton. Whoops. And so in order to get the instance, you have to check and see if the instance is null. And if it's not null, if the instance is not null, it's going to return this instance right here. And whoop. All right. So if it's not, and if it is null, it's gonna return this instance right here. And if it is not null, then it's gonna return the existing instance. So that's how you can ensure that there only be one instance of a class by having a method that does something similar to what you see being done right here in get instance. This is how you ensure that you're always using the same instance over and over again. Even if you call the constructor, you're going to always get the same instance over and over again. And over here in the sum business logic method, this is just another method that would be inside the singleton class, and then you could write additional methods or functionality for this class. But again, it would only, whatever business logic you write, it would always only apply to this one instance right here. You could never create another one. So to recap, we talked about the types of design patterns: creational, behavioral, and structural. And specifically, we talked about the observer pattern, the factory pattern, the flight, wait, singleton, decorator, and chain of responsibility patterns. And we talked about intrinsic versus extrinsic state with the flight, wait pattern, and how we can separate changing versus unique data into our RAM and then in other parts of our memory to speed up our processing or to make our processing power more efficient. We talked about wrapper classes and how we can use them to add functionality to our concrete classes without bloating our code or making it really, messy. And then we talked about use cases of some of these design patterns and why we might want to use them. I think this is a great resource to pick up, from this talk or this discussion. If you go to refactoryguru.com, it just has great graphics, explainers, scenarios, pros and cons, and just pretty much everything that you really need to know related to design pattern stuff. So yeah, I think it's a really good resource for beginners or intermediate, or if you just want to brush up. So I think that'd be a good place to pick up, anything from this talk. So yeah.
Okay.
Let me know if you got any questions. Need me to go back to anything? If not, I'll flip you over.
Oh, sure. No, I mean, yeah, we're a little behind with the things, so it's very hard, So I don't have any questions right now. I think it was pretty good, pretty good talk. The slides are just a little behind, so that was all.
For sure, yeah. Having this lag on the stream. So let me get rid of this and pull yours over.
Wait a little. I mean, because I can't see my slides now. You're still talking about the recap.
Yep, I got you. It's probably a little bit behind. In just a second, you should be able to see the. You should be able to see your slides in just a second. Whenever the stream catches up to where we are right now. Internet connection is crazy. It just says that the stream just came back to like good health. It just went back to green. It was on yellow for a second. So when that starts happening, I'm noticing that it's lagging a little bit, or quite a bit actually. Cause yeah, I have your slides up right now.
Okay, I'm watching. You're coming along. You're at the end now.
What'd you say?
I said I'm watching you now. You're at the end.
Okay. All right, guys. So next up is gonna be Lars gonna talk about operating systems. So I think it'll be a good balance to go back and forth. We talked about some conceptual stuff, and now we're about to get into some really nuts and bolts, lower level stuff. So I think that'll be really good for this week. Good contrast of stuff right here. I'm looking forward to this. And let me know if y'all have any questions. Like I said, leave them down in the comment section if you want me to answer anything about the design pattern stuff or any resources you want me to drop. Just make sure you guys let me know in the comments, and then we'll get back to you. All right, here we go. Finally, on the stream, I'm finally going to put the slides up. Can you see it?
Yeah, I can see them now.
All right.
All right.
It's crazy how far behind that is, but okay. Yeah, let's do it.
All right, so I guess we can move to the first slide. I mean, this is just title operating system.
All right, for sure. Hopefully it doesn't take a super long time because I just flipped the slide, so we'll see how long it takes to.
That's okay, because once we get started, I can tell you to flip early, and I can continue to talk, to catch up.
What'd you say?
So once we get started, I'm watching as well to see how long it takes to flip. I can just tell you to flip early, and I can keep talking until it catches up.
Oh yeah, yep. That'll be a good point. Maybe we'll do that as soon as it goes to this first slide. I'll flip to the next slide.
Okay. You're still talking. You're coming.
Mm-hmm. Appreciate y'all for being patient. Anybody who's out there watching right now through all the technical difficulties, this laggy stream.
Make my screen different too, so I can watch you. I can look at my slides myself, so I can see the process. Okay. And so I'm making adjustments too, so I can work with you.
That's perfect. We always figure it out. That's a good strategy. As soon as the slide flips, you can start talking about your first slide, and I'll just go straight to the second one.
Yeah, let me get my charge. Yep. Yeah.
All right, there we go. So it just flipped on my stream. I don't know if you can see it.
It's flipped to. So this is chapter 1. Chapter 1 operating systems pretty much just talks about what operating systems are, what they're designed to do, and pretty much it. Just an overview, a foundational part of operating systems. So we'll go to the next slide. Sorry, you said you already moved, right?
Yep, already moved. Hopefully it shouldn't take that long now. We should be catching up.
All right, so let me get back behind. So the agenda for today, we're going to just pretty much talk about the major components of an operating system. And we want to describe the organization of computer systems. I'm going to slide forward.
Mm-hmm.
What operating systems do. So I guess pretty much just for me, I think, it was really important for me to conceptually understand that an operating system isn't really a component or a piece of hardware or a section of your computer per se. It's a software application. And the purpose of the software application is to manage your computer hardware. So to manage all the motherboard, the memory. So I thought that was really important for me. I don't know how many people understood that, but I didn't really have a clear picture of that when I first started reading about operating systems. And pretty much the whole purpose of an operating system is to act as an intermediary between your computer user and the computer hardware. That's the purpose of it. There are types of operating systems. We have a mainframe. Primarily, is to optimize the utilization of hardware. We have personal computers, things that we use all the time, and we have our handhelds, like our PDA and personal devices. Some operating systems, again, so I guess as I'm talking about why we have different types, I guess it's important to say then too is that all operating software is different. That is all built for different purposes. I know most of today's users typically use operating systems, whether it's Windows or whether it's Mac OS, one of their systems. But there's all different types of operating systems, and they're all built for different devices. So even the little hardware components, they have their own operating system on them as well.
Were you done with that slide? I just flipped you.
That's fine. Yep, you can flip. That's fine. Well, okay. Yeah. So all right. So maybe no. So I'm still going, but that's cool. I guess what do operating systems do? I guess your computer system itself can be divided into 4 components, pretty much. You have your hardware, you have your operating system, then you have the application programs, and then you have your users. So that's pretty much the layers of how it works, from top to bottom, or from bottom to top. So we have 2 different, I guess, views of our operating system. Of course, we have our user view, which is the GUI, or the screen that you see when you interact with it, buttons and stuff you click. That's a way for you to interact with our operating system. And then from a system view, which is more so, I guess, what developers or computer programmers might view, we pretty much, they're working with the operating system where they're programming the most intimate parts of our operating system. Where you're programming how it's going to interact and interface with the hardware. So this view is a little bit different than the user's view. So you said you moved, so let's go move. All right. Computer system operation. So I guess I don't know how many understand, but I guess it's important somewhat to understand how a computer system actually sort of operates. How does it start and how does all that work? So pretty much when you turn on your computer, every computer has a bootstrap program. That's the first thing that you have, and that's important for your computer to start running. That initial bootstrap program is what it locates and loads into memory your operating system kernel, and then it allows it to start executing its first process, init, and wait for some event to occur. And that's pretty much where it starts up your machine, whether your Windows logo pop up or your Mac logo pop up. That's pretty much how that works. So you have a bootstrap program, which is code, and all this code does is it its responsibility is to locate your operating system software and to load that into your memory, your immediate memory, so that it can start the whole computer working. The computer system, I guess, and we also talk about the operation of it. How I have it here, we talk about the storage structure, and when we look at storage structure, we're talking about memory components. And that's really important, I guess, when it comes down to our operating system and how our operating system operates. On a computer, you have your RAM, your random access memory. You have your ROM, your read-only memory, and you have your FROM. That's your I can't. I'm finding a word for that one, but I'll come back to that. And so those memories are really important because pretty much what the operating system is responsible for doing is moving your program or moving your data from volatile memory to permanent memory, or from permanent memory to volatile memory, so that you're able to view your program to store the data that you need to store. And that's one of the most important functions of the operating system, is to make sure your data is moving from your random access memory to your storage memory, so that so your program can run, your data can be managed more efficiently. Another responsibility of, I guess, an operation is your input-output structure. Pretty much your operating system is responsible for managing it. When we talk about input-output structures, we're talking about your keyboard, video, audio, your mouse. Those are all the ways that we allow the user to input information into the computer, so that we're able to understand what the user would like to do with the program or whatever they're trying to do with our machine. So the operating system, one of their functions also is to manage that structure of input and output, and how we gather information, what takes priority, what happens when a user puts information in using the wrong device, what happens when the device doesn't do what it needs to do. Pretty much the operating system is responsible for all of that. And it's also responsible for our processors. And I guess when we move to the next, processors, we talk about processors, we're talking about our central processing unit. And that's the major unit that pretty much is the brain of your computer, and is responsible for juggling all the responsibilities. So when we talk about processors and operating system, we have two type of processors. We have a single processor or a multi-processor. And a single processor only allows the computer to run one process, which means one application at a time. If another application needs to start, you terminate that application, interrupt that application to start the new application. When you have a multi-processor, you're allowed to run multiple processes at one time. So that's pretty much the difference of that. Let's go back a little bit to our architecture before I move forward to our just our architecture and our storage structures. And in this one slide, I have the storage structures written listed from, I guess you could say, your most primitive to your most most highly developed. So we start with registers, then we cache, then we have our main memory, electronic disk, magnetic disk, optical disk, and magnetic tape. This is pretty much how the type of memory that all computers have.
Wait, is this from? You said what order is this in?
I guess from your most primitive to your highest use.
Okay.
So registers and cache is pretty much so. The operating system usually deals with that, manages how information goes in and out to your registers and your cache, and main memory. As we get a little bit higher on this function, and that's more so different ways where the user is able to interact themselves with memory and store data and store information. And the lower levels is how our operating system is self-managed. Oh, look, you just squared up to me. All right, I'm going to move forward. So unless you have any questions about that?
No, yeah, you go with this slide?
Yeah, I'm good with that slide. Oh, so let me go back really quick to our memory. So we have our random access memory, RAM, which is rewritable memory. And again, it's volatile. Then you have your DRAM, your dynamic random access memory. It's semiconductor technology that implements main memory. Then you have your ROM, your read-only memory. That memory cannot be changed. Only static programs are stored there, like our Bootstrap program that we talked about, where that program is going to do the same thing every time, and that program is responsible for starting our computer. That won't change how that's being done. So in read-only memory, data like that, static programs are held there. It's immutable, meaning they can't change. It's immutable of RAM, you can't change. And that FROM I was telling you about more, so it's firmware. It's within your computer's hardware. It's electrically erasable programmable read-only memory. And the purpose of that memory is because you don't necessarily have to have your computer turned on for that to happen. And why do we need that memory? Remember we said that in order to start our computer, we need the Bootstrap program. The Bootstrap program is a static program that's stored on our computer. And we need to make sure that program starts up and does what it's supposed to do, regardless of whether that computer has the electricity it has or it doesn't. So we store the data with regard to that computer in this type of memory, which in this memory is ran on our hardware. So regardless or not, we're able to start our computer. And again, the memory is small, so we don't store a lot of or significant programs on that. But we will store our Bootstrap program on that. So that was pretty much that about the memory.
All right. So chapter 2, system structures. Did you want to talk on this slide, or you want me to skip forward?
You skip forward. Okay.
Okay.
So in this chapter, pretty much, we describe the services an operating system provides to its users. So again, we'll talk more detail. This chapter talks more detail about that. So I'll just go over the parts I didn't really discuss in the first chapter. Again, these were the first two, the introductory chapters of operating systems. So a lot of information was redundant, just to make sure that you were understanding how and what the purpose of operating systems were. So again, I try to take out some of the redundancy and just talk about the things that we didn't discuss in chapter 1. Also going to talk about the various ways of structuring an operating system. Again, like we said, the operating system is a software, and software is designed for purposes and uses. So of course, the way a system or way software is architected has a major impact on how it's used or how efficient it can be. So there are different ways that operating systems are structured to ensure a more efficiency versus the other. And the last area I'll talk about is the virtual machines. I just think it's really important, especially since you are doing C# and I'm doing Java. So you have a whole section on how these machines work with the languages that we use. So I thought it was very important. I thought it was very interesting. So I wanted to, shout out that a little bit as we go through it. All right. We talked about it a little bit, but we'll go over it just briefly again. The type of services that the operating system offers. So again, the purpose of the operating system, just to reiterate, is to manage your computer's hardware, to manage your computer program. I remember a long time ago when I first learned about computers, they told me that a computer is a dumb box. It doesn't do anything that somebody doesn't tell it to do. And when you think about the operating system, a lot of times as users or even as developers, when we get to the computer, it's already doing so many things for us. And it sort of seems like magic, so to speak. But if you just keep it in mind, it's a dumb box or somebody programmed it, that's when we talk about our operating system. The way our systems work on top of, the way everyone's systems work and how individually they work, all depends on how your operating system was written for your system, for your hardware, for your unit. So it's really important to understand that there is some uniqueness in it. Because of that, operating systems are required to manage both the user and then both your system. So meaning that operating system is responsible for managing your computer's hardware, how your computer operates, how your computer manages data, how your computer manages your memory, how your computer manages all that. The operating system is responsible for that. At the same time, the operator is responsible for your user experience. How do you get your information from your keyboard into your system? How does that data in your memory transpose itself back out so you can hear your audio coming from your speakers? So all these things work hand in hand. The operating system is responsible for both that user view and that system view. And that's when we get that dual mode operation. When we talk about architecting of an operating system, there is architecture in the system that separates the two, because the system view is more of a kernel view. And that view means that if you have the wrong person inside that, they're going to damage your computer because it's controlling the hardware, how the computer functions, and your computer will no longer be useful to you. So it's very important that we separate the sensitive data from people who don't need that data. We sort of encapsulate it. So the operating system is responsible for encapsulating that data to keep this kernel and the system and information that's important for our computer to run away from people who don't need to access to that information. At the same time, provide a way that people who do need access to things like how we put information in, how do I put in my games, how do I fill my files, we give them access to that stuff, and we separate and we restrict it with security. So operating system is responsible for dual mode operation. Mm-hmm. Timer. It's important just to understand timer, just to keep track of the system, keep track of the functions, keep track of the processes, keep track of everything. So, most systems always have this Unix time or time from when the first keeping track of time. That's pretty much what this part is. How do we keep track of things? There's a lot of things in the operating system itself that does things off of timers. Like I know in most of our code, we do things like the set time out. So if you think about that concept where you're doing something, you're saying every 5 seconds, I want you to redo this function or redo this. It's the same type of dynamic that happens within our operating system. There are certain things that have to happen at a certain time. There's certain processes that start, and we need to make sure they finish at a certain time and make sure that they allow something else to happen. So within it, it has to have a system of a timer to be able to keep track of these different situations so we can manage them accordingly. Process management. We talked about that single and the dual, and so it has something to keep track of the processes, the multi-thread usage and all that. Operating system is responsible for that because all these processes require memory. They need a place to store the data. So operating system is responsible for managing all those processes that happen on your computer all the time. Memory management. We talked about that. It's one of the most important things that operating system is responsible for. How do we store our data? Where do we put our data, and how do we get access to it? We have this concept of virtual memory. We have the concept of random access memory, and we have the concept of maybe story memory. That's not the right word for it, but I guess it's a memory that we put in storage, so to speak, that we have to go away, and it's not volatile, it's not hard drive memory. The operating system is responsible for managing all those different types of memory. I'm trying to understand when is the application being used, and we need to put it in a random access memory so it's quick and people are able to access it. How do we understand that? Okay, you got to keep a timer on that type of application. Keep mindful of use. I don't know if you've ever been on a computer and your application timed out, and because it timed out, that meant that it moves it from that random access, get quickly access it to another area on your computer because you're no longer using it.
Oh wow.
Operating system is also responsible for caching your stuff. We're trying to figure out what programs it should cache and what programs it shouldn't cache based on how you're using your programs in your system, so that some programs, so you go between from program to program, you go back to where you want to go very quickly. That's because your operating system is caching what you're doing and is allowing you to be able to do that. Storage management, it sort of goes in line with that. Memory management, like I said to you, just trying to manage where should data be held, where should memory be stored, what data should be held at, when should we, how do we access data, in programming there's times where we want to point to different data, we want to overwrite data, pretty much that. Operating system is responsible for all that stuff. Like, how do you know where your stuff goes to memory? Who determines that? Who determines when things are getting written over and when things aren't being written over? How do we determine why things are stored where so we have better access to it in a quicker time? Like, this is all we operating system is responsible for, and make your system run as smooth as possible. We talked about the input and output, so I'm not going to go over that again. And finally, the protection and security. The operating system is a very powerful system. So it has to be a lot of protection on, like I said before in the beginning, for a lot of different reasons. One, from users who don't really know about tech like that. You don't want them to have access to certain parts of their computer they will destroy. Also from outside people. As I move on in the lecture, in the conversation a little bit more, we'll talk more about virtual systems and things like that. And even we talked last week about networking. When you connect to a network, you're opening part of your system up to someone else. So you have to have some type of protection and security so that when you do connect the network to other systems, you're not exposing all the most sensitive parts of your system to other people, and other people can't take advantage of that. So the operating system is responsible for that. When I say operating system is responsible, I don't want to make it seem like a system is itself. No, whoever programmed or built your operating system, the human who wrote the code for your operating system, they are responsible to make sure that your operating system can take care of all the things that we talked about on that list 1 through 7. Those are the things that make your operating system a good operating system and make it safe for it to operate and succeed. Design patterns. So like everything else, operating systems have their design patterns as well. We'll go over these briefly. So the first one pretty much is just your simple structure, I guess, how you would, let's go back. The goal of the simple structure is to make sure is to understand that you want to build the operating system that's simple and structured. You don't want to build this operating system that's very difficult for people to understand, for people to use, or for difficult to maintain. Again, the operating system is responsible for your entire computer, so you want to make sure that when you build something that's simple for everyone to use, and not just for just simple for everyone to use. Okay, so moving forward. So layered. So this concept is sort of like the concept of the network, where you build your most basic, your most primitive responsibilities at the highest level. You I guess at the bottom level, at the lowest level, you build your most basic. the things that your operating system has to do all the time. And then each level, like the networking system, each level is only responsible for what its functions are and what it passes on to the next level. The problem with building an operating system like this is that A, it's a little bit slow because you have to go layer to layer to layer to get the processes working. And two, the problem is that if a programmer forgets to build something, or you need something that's in another level and you're encapsulated away from it, it's going to make it hard for your operating system to work. So I guess in overall, they're saying that the layer system is difficult, not because the system or the pattern design itself is difficult, because it requires a lot of responsibility on the programmer to make sure that you're programming things in appropriate layers that they belong to, because layers aren't able to move information throughout each other. It's only responsible for the information and passes to the layer above it. So if you don't put the information that you need to put in the right layer, your operating system will be limited on what it's able to do based on it being encapsulated away from certain information it needs on certain layers. That makes sense. The next sort of diagram is the microkernel. And I guess for this idea, sort of the idea or the structure of this was that, they figured that that kernels, once you continue to expand them, they became very, very large and very difficult to manage once that happened. So they wanted to develop a solution where you can expand your kernels, but you can keep them in a way that you can sort of control them. When we talk about kernels, we're talking about that part of the operating system that does all the controlling of your system, of the hardware, and of your core system. That's pretty much the kernel. And that's the important part that's going to allow you as your operating system to do multiple things, multiple things. And when you get to the virtual world, you'll start to see more what I mean when I say multiple things. So I guess part of the function of this microkernel thing was to provide communication between the client program and the other services that the operating system sort of provided. It wanted to be that medium, the medium to be able to communicate between the two. And I guess operating systems always do it, so one might want to know, why is that important and why is that a benefit and why do we need to do that? Because I think, like anything else, we need to be able to scale. Everything in tech is about scaling. How do we use these operating systems in different ways to allow us to solve different problems? And if we have to add things on and make these kernels so that they're too big and we can't do much with them, then it limits our ability and limits the amount of choices we have to problem solve. So the microkernel became very important because it allowed us to add more functionality to our kernel as we move forward. And as we move forward with the virtual systems, allow us to do other things as well that's important with the operating system. The most important, the final type module is pretty much the most common one that's used. It's used in most of our Linux systems. Going back to your microkernel. The first Unix, Unix 264, they use a microkernel called the Mac kernel. The Mac OS X uses a kernel, also known as Mac OS X, known as Darwin, that uses the Mac kernel. So those are two, there's two products out there that's currently using that kernel type of operating system. The final operating system was a module, and almost every operating system today uses the module as opposed to the other one. And the module is sort of simple, how we know about modules and regular design patterns as software engineers. It's pretty much a way of dividing your code in a way where you can add things to it and you keep it and you divide it by its single responsibility. So you're responsible for this, and we can add to it. So right now, a lot of our operating system pattern designs are designed in a modular form, where responsibility is sectioned off into modulars, so that if you want to add or take away functionality, you can do it very simply without impacting the other areas of your kernel system, so to speak. All right, and our final talk today that I want to go over briefly is this concept of a virtual machine. The concept of a virtual machine is really pretty cool. Some of the stuff I don't really get into detail as deep as I probably could when we talk about this stuff, because in all of these books, as I realized, now that I'm past all the introductory chapters, we're going to be spending a whole chapter talking really in deep about all these concepts. So I'll probably go over these things again. This is just a brief overview, just to expose people to what we're talking about. And, if any questions you have, we'll hopefully cover as we move forward. So it didn't really talk a lot about the virtual machine, but it did. I thought one thing that was really interesting with the virtual machine is what a virtual machine is and what I thought it was. I didn't really, a virtual machine. I don't know what I thought it was, but pretty much, I guess, as I realized, it's just another operating system. So I guess what the theory is that on our current, whatever you're on, whatever type of machinery you're on, there's a limit based on what your hardware capacity. But in general, your current system now could run as many operating systems as you need it or want it to run. There's nothing that stops it, because if you think about it, an operating system is only a software program, no different than Windows, no different than chess, no different than any other application program that we run. That's all the operating system is. So there's no reason why we can't run 3, 4, 5, 6, 7 different operating systems on our laptop or on our regular computer. And if we're able to do that, imagine the different type of application, imagine the type of space and efficiency we're able to create, and we're able to duplicate or even quadruple how many operating systems we're able to run off of one system. So what a virtual machine does, the only thing that would stop us from doing that is that, remember, our operating system, one of its main functions is a bridge between the computer hardware and what the user does. So even if we put 5 or 7 different operating systems on our computer somehow, we only have one set of hardware, right? So we need to make sure that operating system, or all 8 of them, understand that they're still operating the same piece of hardware. So this is where this whole idea of virtual machines come. And what you're doing is you're tricking your computer to thinking that it is 4, 5, 6, or 7 different pieces of stuff. So that virtual operating system that's running on your computer thinks that there are 10 different pieces of hardware where there's only one. Mm-hmm. And how do they do that? They do that with a layer. They put a layer there, where a layer of software or API or interface that acts like that, an interface that acts like that between your actual system view, your kernel, and your virtual machine layer. And that interface provides functionality to that virtual machine layer that makes your virtual machine believe that there's multiple, of course, because it's an interface, so every time a virtual machine, you have 4 or 5 different operating systems, every time they hit that one interface, they're only locked in on that one interface. That one interface for them represents whatever hardware it has, even though it's only one system. Those 10 different interfaces makes the software believe that there's 10 different systems. And that's pretty much how virtual machines work. Now, there are different types of them and different variations of them, and I'm not going to get into all that detail of it, but for more or less, that's more or less how they all work. And the interesting thing. So I guess what was interesting to me was, I didn't really hear a lot about .NET, but I guess .NET is very similar to the Java virtual machine. But I've always heard about the JVM. I've always heard about how, Java is very good because it's portable, and the JVM's on everyone's computer and blah, blah, blah. And I didn't really understand what the JV meant. I'm thinking it's some type of software that, it's just software that is on everyone's system. Now, I guess going through this chapter lets me understand that a JVM is a virtual machine. So yeah, it's software, but what they're saying is that on everyone's computer, when we put that JDK, whatever that is, software Java program on it, we're adding a layer of software on our machine that provides an API so that we have that Java virtual machine right before our layer of our kernel. So if we go down, we have an application, we have our virtual machine, our Java virtual machine, then we have our operating system kernel, and then we have our hardware. So that's pretty much how it works. And it works the same way with .NET. So you have your application, then you have your .NET virtual framework. That's not the name of it. It's a real name for it, but that's not the name of it. Then you have your Java. Then you have your kernel, your operating system stuff, and then you have your regular operating machine. So without getting into all the details of it, definitely want to leave something for you guys to go and read it your own. But with the Java virtual machine, with the .NET machine does is show in languages, right? So we talk about our computer hardware. Our computer hardware reads machine code. It reads the assembly level code, the byte code, zeros and ones. So when we talk about the operating systems are written in C or C++. And that's like a low-level language that helps the operating system manage hardware, communicate with hardware. So once we get lower than C, we're right there in assembly language. There's nothing lower than C but assembly language. So when we run a program on our system, we need a compiler or an interpreter to compile our code and turn our code into code that we turn our code into the machine code language so that they can understand and we can read to the machine. So that's pretty much how it works. But with the Java, so and the problem comes in is that if you're transporting if you're compiling your code into machine code, every machine has different hardware. So it's very complicated to do that without having a certain type of compiler. So that's why most languages have a compiler. What makes Java and .NET very unique is that these things come on, so I guess .NET must come on Windows programs, and Java comes on virtually all machines. They're all these virtual programs. So what happens is that no matter, every time you have a Java code, what happens is it doesn't compile down to machine code. It compiles down to bytecode. Then it's transformed into some other type of code that Java does. And then that code connects to the machine and to everything else. And the same exact process happens with .NET. So I just thought that was very interesting. Like I said, for me, dealing with Java all the time and dealing with JVM, I didn't really understand that to that level of what is actually a virtual machine. It's actually a virtual machine that's on your application at all times, and that's why why it's portable, quote unquote, and why you're able to use your Java program there. I just thought that was pretty much interesting. But that's all I have for today.
Nice. Well presented. This is really good. I'm gonna go back and look over some of this stuff myself. I think it's good how you simplified those 2 chapters, because those chapters are really, really dense in that book. So I think this is a really good condensed format for it. I'm gonna swing back over to Skype real quick just to so we can close out real quick. Exit my live demo. All right, cool. So I just swung back over to Skype. So yeah, that was really good. I think that was really, really informational. So what's coming up? Are you going to keep going with are you just going to stay with the operating system book and just read through it?
Yeah, I think I'm gonna read on both. I think next week I probably would touch on just more detail of maybe the languages, or either I might touch basically on the languages, a difference between your high level languages, your low level languages, difference between a scripted language and it's not non-scripted language, just to talk about the differences between those, or I might talk about continue with my operating systems to talk about my Linux, my Bash compiler thing. So I'm not quite sure yet, but I guess I definitely will have something for you guys next week. Definitely be interesting. So I'll definitely let you know.
All right, for sure. Yeah, that sounds good. I'm torn between like some more NoSQL stuff and networking, because I think that scenario based stuff about setting up a network is really, really interesting. And that'll give me a reason to do some research into like the hardware stuff behind the switches and routers and all that good stuff, because it didn't sound like it was incredibly like hard if you knew what you were doing, but it just sounds like knowing what you're doing, like knowing all the different things you need. So that'll be cool. So it'll be somewhere in there. I think it's gonna be somewhere in the networking side though, and maybe some database stuff too. So that'll be good. Look at this guy.
Walk.
All right, for sure. Well, I appreciate your time, La. I think we finished right on time, like just over hour 10. It's perfect. So thank y'all, anybody who is here with us, and again through the laggy stream and any difficulties we have. But we'll catch y'all next weekend.
All right.
All right, for sure. I'll holler at you.
Yep.
All right, see y'all.